We would like to present our paper Progressive Semantic Segmentation in CVPR 2021. Image semantic segmentation is the task where with an input image, the model needs to classify each pixel to the predefined categories. In high-resolution semantic segmentation, the input image is in a very large size, more than 4 million pixels. This task causes the memory to explode when feeding the whole image to the model. There are two typical approaches to this task, namely downsampling and patch processing. In the downsampling, the high-res images are rescaled to a smaller size which can be fed to the memory. The output of the model is then rescaled back to the image sizes. This approach is practically used due to the low latency in inference and acceptable segmentation accuracy. However, during the downsampling, the details are lost and the received results are coarse. In patch-based processing, high-res images are divided into smaller patches that can be fed to the memory. A set of predictions, after processing, are ensembled to a high-res segmentation map. Due to keeping the image resolution, the gain segmentation map is very fine-grained. However, the processing time of this approach is large, and this framework will fail to detect large objects when each patch contains a part of the object. Now, we will take a look into the overview of MagNet, our proposed method which can produce high-quality outputs for high-resolution semantic segmentation task. At a scale, the input image is divided into patches. Each patch is then resized to be feedable to the memory. We obtain the scale-specific prediction by any segmentation networks. The refinement segmentation map is produced by the refinement module with both information from, first, scale-specific prediction and second, the corresponding cumulative segmentation from previous scales. The process applies to all patches before upsampling and ensembling to reconstruct the high-resolution segmentation map. In the next scale level, we apply the same strategy on smaller patches to obtain more fine-grained details. The framework refines the segmentation map from the coarsest level, which patch size is the whole image size, to the finest level, which patches are in the memory storable size. With this multi-scale and progressive refinement architecture, more details have been added to the segmentation map without being too global or too local to a specific scale. The refinement module is a core component of our framework. The input to this module is two segmentation maps, namely scale cumulative segmentation map Y from all previous steps and scale-specific segmentation map O from the current scale. These two segmentation maps are first combined and then used to produce an early refinement segmentation map R. With the uncertainty maps of Y and R, we compute the ranking score Q of each location in R. With this Q score, K locations on Y are selected to be replaced with corresponding new predictions on R. At the end, we have refinement output which contains information from both O and Y segmentations. For each pixel on Y, the prediction confidence is the absolute difference between the highest and the second highest probability values. The uncertainty score is computed based on the confidence score such that the two scores must add up to 1. The Q score is calculated by this formula. It's a point-wise multiplication between Y uncertainty and R confidence score. The output is then smoothed by the median blurring. We propose another fast version of MagNet named MagNet Fast which runs on a smaller number of patches. MagNet Fast refines on fewer number scales and top uncertainty patches. Therefore, the number of patches processed by MagNet Fast is smaller than this number in the patch processing approach. To prove the effectiveness of our proposed method, we run on 3 different higher-resolution datasets: Cityscapes, Deep Globe, and Gleason. This table shows the performance of our framework. In the Cityscapes dataset, the MagNet can improve by approximately 4% from the downsampling baseline. In the Deep Globe dataset, both MagNet and MagNet Fast yield better mean intersection over union than GLNet and PointRand. In the Gleason dataset, dense CRF performs well on this dataset, but the inference speed is incredibly slow. In this example, the downsampling produces a coarse prediction when all small objects like poles are missing. All previous methods can improve the segmentation result, but they are not perfect. Our MagNet and MagNet Fast can edit boundaries and recognize new tiny objects at the same time. These are some other results on the Cityscapes dataset in comparison with SegFix and PointRand methods. On the Deep Globe dataset, we show here some results. On the Gleason dataset, we show here some segmentation results where the MagNet works well on these histopathologies. In conclusion, we have introduced a novel semantic segmentation framework for higher resolution. Please scan this QR code or go to this link to investigate more about our framework. Thank you.